Today would be discussing about something a little bit different, which is the 8-bit floating point representation. And why would we learn this? So this floating point representation would help us to convert any floating point number to a binary representation. So the higher the bit number, the more accurate the representation would be. So before diving into how it works, we have to understand some theories or some basic concepts. The first one we'd be covering is the decimal to binary and vice versa conversion. So from your early courses or your school lectures, you might remember that to represent any binary number to a decimal number or a decimal number to a binary number, we have a cheat, which is writing this. So 1, 2, 4, 8, 16, 32, and let's say you want to represent 35, a decimal number, and you want to represent it into a binary number. So the process is we write 1 for 32, so we are taking 32. Then we cannot take 16, we cannot take 8, we cannot take 4, that would be too much. And we can take 2, so that would be 34, and 1, that would be 35. So this is the binary representation of 35. There's another way. So this is the basic way of converting any decimal numbers into a binary number. How about when we convert any binary number into a decimal number? So this is a binary number, and now we want to convert this into a decimal number. So you can use this format to do the conversion. So that would be, we're taking 1, 2, 4, 8, and we have 1, 1, 0, 1, right? So that means we would be taking 8 plus, we would be taking 4 plus, not taking 2 because that's 0, and would be taking 1. So that is 12, that is 13 here. However, there's another way to convert this. So that is the multiple of 2. So 1 into 2 to the power 4, sorry, 1 into 2 to the power 3. So I'm writing this using this. So any number before the decimal point, so every number has a decimal point, right? Like an imaginary one, so that is 0, 0, 0 something. So we do not write this, we just write the main number. So similarly, this number also has a decimal point, like an imaginary one that has after the decimal point we have zeros. So before the decimal point we have 0, 1, 2, 3. These are the numbers for each bit. Now to represent that, we have 1 into 2 to the power 3 plus 1 into 2 to the power 2 plus 0, because we have 0 here, into 2 to the power 1 plus 1 into 2 to the power 0. And this would, doing all the calculations, this would be 8 plus 4 plus 0 plus 1. So this would give us 13. So see, both of them are the same. In this example, like this one, we have to find the index numbers of each bit and then multiply it with 2 to convert that decimal number into a binary number. And how about for numbers that are after the decimal point or the right side of the decimal point? So the process here is, the index number are a bit different. They start from -1, -2, -3, and so on. So let's look into another example here. So if we use the second method that we talked about, then that would be any numbers on the left side of the decimal point. We start from 0, 1, 2, and 3, and on the right side we have -1, -2, -3, and -4, and then -5. Okay, so let's do the calculation for this. So this would be 1 into 2 to the power 3 plus 1 into 2 to the power 2 plus 1 into 2 to the power 1 plus 1 into 2 to the power 0, then plus 0 into 2 to the power -1 plus 0 into 2 to the power -2 plus 1 into 2 to the power -3 1 into 2 to the power minus 4 plus 1 0 into 2 to the power minus 5. So this would give us, so this whole calculation would give us 14.1875. that is a decimal number. So this is the basics of how to convert from decimal to binary and vice versa. Now we are going into 8-bit floating point numbers. So 8-bit floating point numbers, they look like in this format. So 0 0 1 0 1 1 0 1. So this is the format that they follow. So these are total of 8 bits here, and the first bit represents the sign bit. So for the sign bit, 0 means it's a positive number and 1 means it's a negative number. Okay, so these 3 numbers or these 3 bits represent the exponent, and these 4 bits represent the mantissa or the significant, whichever makes you comfortable, whichever you know. However, there's another division here. So if you write the number again, so 0 1 0 1 1 1 0 1, these 4 bits represent the floating number, and these 4 bits represent the integer portion. So this is what like the basics of 8-bit floating points is. Now we're going to learn more about mantissa. So mantissa is basically the significant portion of the floating point number. So remember when we write the value of pi, that is 3.1416, and it's a huge number, right? Similarly, whenever you do calculations, we have like huge numbers after or on the right side of the decimal point, right? 4 2 3 1 6. And whenever we are like writing the answers, we do not write the whole thing, right? We just write the significant portions. Let's say like up to 4 or up to 5 numbers. So these 4 or 5 numbers, these are the significant numbers, and these are called the mantissa or the significant, rather than, because the numbers that are going far to the right, they are not that significant, they do not make that significant of a change into the number. However, the numbers that are much closer to the decimal points are more significant and have more value to it. So that is all for significance or the mantissa. Now we'd be going through another topic, which is type of numbers. So numbers are basically of 2 types. The first one is the normal number, and the second one is the subnormal number. So normal numbers are of this pattern. So there will be 1 dot some fractional value to it, and subnormal numbers are basically 0 dot some fractional value. So the difference is basically in the integer portion. Normal numbers have 1 and subnormal numbers have 0. So the formula for normal numbers is basically this one. So minus 1 to the power sine into 2 to the power e, which is the exponent value that we would be getting from the 8-bit, minus 3 or minus n for this case, into 1 dot some fractional value. And when it comes to subnormal numbers, the formula is minus 1 to the power sine into 2 to the power 1 minus some n value into 0 dot the fractional value. So this is the format. Now whenever we are writing the exponent value, so let's say 0 1 0 1, so this is the sign bit, right? So the number would be definitely a positive one, and this is the exponent value. So for this case, if you remember how we converted decimal binaries to decimal number, we can do it using 2 multiplication, or we can just go simple and cheat, and 1 2 4. So this represents basically 5. So what we would do for normal numbers, we would have minus 1 square into 2 to the power. We said that we need the value of e, right? So e here would be 5 minus 3 into 1 and some fractional value here. So what's the point of this 3, and why are we writing 3? So for 8-bit numbers, the trick to find this number that's going to be here, so we said that there is an n value. So the trick here is to see how many bits are there in the exponent. So in this case, for 8 bits, there are 3 bits, 8-bit representation, so there are 3 bits for the exponent. So 3 bits can represent up from 0 up to 7, where 7 is the max one, right? Now you can divide 7 with 2. This would give you 3.5, and then you float the value, it would give you 3. This is basically the technique that you follow in this case, and this is basically a cheating way to find out the value of n. However, the actual method is 2 to the power the number of bits allocated, which is 3, minus 1 minus 1. So this would give us, so for the 8-bit representation we have 3 bits for the exponent, so this would give us 2 to the power 3 minus 1 minus 1, which would be 2 to the power 2 minus 1, which would be 4 minus 1, and would give us the value 3, which is similar to this one. So whenever we are dealing with, let's say, 16-bit representation, then we have 4 bits for the exponent, right? So the formula would be 2 to the power 4 minus 1 minus 1. So this would give us 2 to the power 3 minus 1. That would be 8 minus 1 equals to 7. So we would have to do 2 to the power e minus 7 for an 16-bit representation. So moving on. So there are some weird cases that we need to understand before diving into some examples. So as I said, this is the format that we follow, right? So for 8-bit representation, where this represents the exponent and this represents the mantissa, and this is basically your sign bit. Now in the case where you have triple ones, or 1 in each bit of the exponent, and 4 zeros in the mantissa, then the number would be an infinity. However, in a case that we have triple ones in the exponent, however some value in the mantissa, then that would be not a number. So this is just the weird case that we need to look into whenever we are doing the code or whenever we are solving any problems. Now let's just dive into some examples and see how things work around here. So in this example, this is the 8-bit representation that is given to you, and in this representation now you have to convert this number into a fractional number. So from the looks of it, we can completely understand that this is definitely a positive number, and the value of the exponent is 0. So as the value is 0, that means that it is a subnormal number, And this is the one thing that I forgot to tell you. So if the value of the exponent is 0, then that means that the number would be definitely a subnormal number. And however, if the number it has some value into it rather than being 0, then it is a normal number. So for this case, this is a subnormal number, and this is the value of the mantissa. So let's just put this into the equation that we are working with, and let's get on to it. So this is definitely a positive value. Then we are doing, so remember, for subnormal numbers the equation was 2 to the power 1 minus n, and as this is an 8-bit representation, so we would have 2 to the power 1 minus 3 into 0 dot some fractional value, and now we have to calculate the fractional value from the mantissa, and the process is 1 0 1 1. And remember, I told you that any number after the decimal point would start from -1, -2, -3, and so on. So this would be -1, -2, -3, -4. So 2 to the power 1 into 2 to the power -1 plus 0 into 2 to the power -2. So you can just not write the value for the 0, or not write 0 at all, plus 1 into 2 to the power -4. So this would be giving us 0.8125 if we do all the calculations, and we put the value here 8125, and doing all the calculations we get 0.203125. So this is the fractional representation of this 8-bit number. Now let's look into our normal number example. So this is another example that we'll be looking into, and remember, in your exams, whenever you're given an 8-bit number, always try to put them in this format, so that's easier for you to identify which is what. So for this case, we have a positive number, as 0 means that it's positive, and for the exponent, as it is not 0, so it's not a subnormal number, so it would be definitely a normal number. And this is the exponent value, and the value of the exponent would be, so the same procedure that we followed, so either multiplying it with 2 or using the cheating method. That would be 1 2 4, so this would be basically 1, and this is the mantissa. So let's just put the values into the equation, and let's see how it goes. So this is a positive number, definitely, so we're going to put a positive sign in front of it. A positive number, 2 to the power, so the exponent value here is 1, so 1 minus 3 into, so as this is a normal number, so it would definitely have 1 and then some fractional value, and we're just going to calculate the fractional value here. So 2 to the power 1 into 2 to the power -1, so this is -1 -2 -3 and 0, so -1 plus 1 into 2 to the power -3, and after calculating the whole thing, you would get 0.40625. So this is the final example that we will be looking into, and let's just write that in a easier format so that's understandable. Now as this is 1, so the sign is negative, and the exponent is not 0, so it would definitely be a normal number. So the exponent value would be, so let's just follow the cheating method, and this would be 1 2 4, so this would be 3, and this is the mantissa. So just put the value into the equation. So this is a negative number, and 2 to the power, remember the equation, 2 to the power e minus n, and in this case n is the, so n is basically 3, and that would be 3 minus 3 into, as this is a normal number, so 1 point some fractional value, and the fractional value here would be -1, -2, -3, -4. So 1 into 2 to the power -1 plus 1 into 2 to the power -4, and this would give us the value of -1.3125. So hope you guys did understand this long video and all the basic concepts of 8-bit representation and how do we convert any fractional number into a binary representation and vice versa. So if you have any questions, definitely leave it down below and give a like and subscribe to my channel for more contents like this. And thank you.